since this is a bit further than you're used to, so we can all get here on time. All right. All right. Here's the rule about the prerequisites. It's the usual rule I have, which is these are strongly recommended. If you don't have the prerequisites and you want to take the class, that's okay with me, but the onus is on you to make up the background material, because I'm just going to proceed assuming you know all the material in these courses. The notes from 705 are still online if you want to look them up. And 701 or 715, I'm sure you can get the notes fairly easily. But I assume you know that. So things like convergence and probability, weak law of large numbers, convergence and distribution, the central limit theorem, these are things I'm just going to assume you're familiar with. Maximum likelihood estimation, Fisher information. Those things should all be very familiar. Regression, what's the basics of regression? What's the basics of classification? So these are all things, again, I'll just assume you know. I mean, we'll review things as needed, but if you haven't seen them before, it's going to be difficult. There isn't a book, but I will post notes online. And right now, there's 2 or 3 sets of notes already there. So when you go home, you might want to download them or at least put them on your computer. There are some books that are good background. I think Hasty, Tibshirani, and Friedman, The Elements of Statistical Learning, it's missing a lot of the theory that we're going to cover, but it's a very good book, and the PDF is free online. There's an older book, but it's still very good, by DeVroy, called A Probabilistic Theory of Pattern Recognition. One of my favorite books about the theory of classification. It's 20 years out of date, but the material in there is timeless. It's got really good stuff about VC theory and so on. Now we're starting to get... Okay. So, and that, I'm pretty sure, like, it's a Springer book, and I think most Springer books are available, the PDFs, for free on campus. So you can get that book too, and I would really recommend that. That's a great book to have. Another book I forgot to mention here is the book by Sasha Sibikoff, also a Springer book, so I think you can get the PDF for free. It's a book about non-parametric estimation. It's a very slim volume, beautiful book, great, clear proofs, and we'll be using a lot of the theory when we get to minimax theory in that book. Okay. So the grading will be a bit different than in 705. We're only going to have probably 4 or 5 assignments. I see the disappointment already. But don't worry, we'll make them longer. So we'll keep you happy. My office hours are Tuesdays after class, but there's 3 TAs. Did any of the TAs come? Probably not. The TAs are Jisoo, Brian, and Adams. And their office hours will be posted in the next day or two on the web page. Okay, so all 3 of them will be having office hours every week. There are seats if you want to, if you're not comfortable on the stairs. Like there's a couple here in the front, one over there. Feel free to squeeze in there. Okay. The course assistant is Mallory, and she's in Gates Hall 8001. So she'll collect homeworks just like Mary Alice did last term. Homeworks will typically be due Fridays at 3 o'clock. And so the usual, just like we did last time. And as in 705, if you have a legitimate reason, like illness, that you can't hand in on time, that's fine. Just let me know ahead of time, before the deadline. All right. So the grading will be, there'll be 1 midterm only, and that's 25%. there'll be 50% for the assignments and 25% for the project. I'll describe the project in a moment. Let me say something about the topics we're going to cover. So the idea here is this is supposed to be advanced statistical machine learning. So it's building on 705, the math stat course, and on 701 or 715, which are more method-oriented machine learning courses. And the idea here is to do a mix of methodology and theory and understand the theory behind a lot of the machine learning stuff. And over the years, I've played around a lot with how to cover the material in different orders, and I've really gone back and forth. This year I'm doing it differently than we did it last year. So I'm going to start with some theory this year. Last year we plunged right into basically non-parametric regression and non-parametric classification. Then we did the theory. This year I want to do it the other way around. So I want to do some theoretical preparation first. So first is, hi, come on in. We're going to start with a bit of stuff on function spaces. What I mean by that are classes of functions, and it's not that we need any deep stuff. This isn't a course on functional analysis. We don't need any deep material about function spaces. But the reason why we're going to have a little short lecture on it right in a few minutes is just because last year students pointed out that when Ryan taught the course with me last year, when Ryan and I were teaching, we would often refer to a Holder space or a Sobolev space. We never really defined them, and that was a bit confusing. And so the purpose of covering function spaces is we're not going to go into a lot of detail about them, but we should start off all kind of with the same vocabulary. It's just to establish definitions, really. The main spaces you need to know about in most machine learning stuff and in most statistical theory is what's a Holder space, what's a Sobolev space, and what's a reproducing kernel Hilbert space. So we're going to go over that today. And again, we don't need a lot of deep theory about it, just basically what are they and what are they used for. And it's just because we're going to refer to them. Then we're going to do concentration of measure. We hinted at that in 705. We did Hoeffding's inequality, you remember, which said basically that an average is close to the mean with high probability. And we also touched a bit on VC theory, which was extending that in a uniform way, but we didn't prove anything. So this term we want to talk about how do you prove the main VC theorem? What are the techniques there? They're really good. It's the kind of proof you should see once in your life if you've never seen it before, because the techniques that get used in that proof get used all over the place. If you look at a lot of the theoretical papers in NIPS, for example, those tricks in that proof get used quite often. And something called Rademacher complexity, which comes up a lot. Okay? Some of you have heard of these things before. Some of you haven't. That's okay. We'll do it from scratch. So that'll be probably what we'll cover this week and maybe next week. And then we're going to go back into more methodological stuff, which will be supervised learning first. And so what is that going to mean? It's going to mean, first of all, high-dimensional regression. How many of you have seen the lasso? L1 regularized regression. Virtually everybody. Okay, so we'll look at the lasso, but what we want to talk about are what are the theoretical properties of the lasso? And what are those properties that you can trust? And some of them are good properties. Some of them are properties that are very fragile, that depend on very unrealistic assumptions. So we want to understand the difference between sort of the reliable theory and the unreliable theory. And then we want to do the same thing for non-parametric regression. How do we do non-parametric regression in low and in high dimensions? And what's the theoretical properties of these things? Then we'll probably start unsupervised learning. Then we'll do the same thing for classification. Then we'll start unsupervised learning, which will be non-parametric density estimation. We did a little bit of that in 705. We'll do a little bit more now, talking about the theory. And then we're going to plunge into something that I alluded to a lot in 705, which is back to minimax theory. So in 705, we talked about minimax theory for parametric models. But really, the most useful part of minimax theory is for non-parametric models. So when you're doing classification or regression or density estimation non-parametrically, how do we know when we've got an estimator it's the best possible estimate? How do we know there isn't a better one? And as usual, remember, we answered those questions with minimax quantities. So just to remind you, if we're estimating something, well, now I'm going to make it a function. If I'm estimating a function with an estimator f hat, we looked at quantities like this, where we would look at the risk. That's a risk over some large class of distributions, and then we took the inf over all estimators, but we only did this for parametric problems. So the techniques for finding minimax risks like that for non-parametric problems are quite different. And we'll talk a bit about how to do that, and we'll prove some of the more famous results that come up quite a bit. And then we'll go back to methods again. And then at that point, I want to see where we are and what people want to cover. We have quite a bit of flexibility. Probably we'll do a lot of clustering, graphical models, and then I have a whole variety of possible topics listed, which I may or may not cover. I just sort of did a laundry list: non-parametric Bayes, more high-dimensional bootstrapping, adaptive data analysis, robustness, active learning, differential privacy. I put deep learning in there. I don't know what I'm going to say about deep learning, but I thought I'd throw it on the list. So there's all kinds of potential topics we can cover. Now, in previous years, I've often team taught this course. So last year I did it with Ryan Tibshirani. Decided to give Ryan a break this year. So his wife was getting mad at me that I was working him too hard. So he may come in and give a few guest lectures, but for now, I told him to take a little breather. And there'll be one or two other probably guest lectures throughout the course. We'll see. All right. The calendar is on the web page, so make sure you go to the web page. That's going to obviously change. So I have there a prediction right now of what we're going to cover every day, but it's going to change as we go along. More importantly, it has when all the assignments are due and the project due date. So let me tell you about, and the project milestones. So let me tell you about the project. The projects have been a lot of fun in past years, and I think the students have really liked them. And it's a little bit different, though. If you did 701 or 715, you probably did a project of some sort where you took some method and applied it to some interesting data set. But this is a theory course, so it's going to be a little bit different. So we really are running out of room, aren't we? Okay. Are you guys okay there? Do you need me to kick 6 people out so you can get seats? There's one seat here. There's another seat there. There's another seat there. Another seat there. There are actually 5 seats. Unfortunately, people keep coming in faster than I find seats. So by the end of the class, we'll talk about space issue. I told Jeff Gordon, though, that next year we're going to need a bigger room, I think. Because I think we actually did have a larger room last year than we have this year. I'm not sure why. Okay, the project. So the project's a big chunk of your grade. So here's the idea. What I want you to do, since it's a theory course, I want you to pick a topic and something you're interested in. And the idea is this. Imagine you picked the topic you're interested in. Just to pick something, let's say support vector machines. You suppose you're interested in support vector machines. And suppose somebody asked you, look, I need you to write a review paper about support vector machines, and in particular about their theoretical properties. And so what you'll end up doing is, the idea is throughout the term I want you to find some papers, read the papers, and then write a nice crisp review paper which summarizes what are sort of the main theoretical results that are known about this particular topic. Let me say something right now that I get asked 20 times throughout the course. No, you do not have to produce new theoretical results. Okay, this is not your thesis research. This is just a class project. So no, you don't have to produce any new results. If you want to, that's great. Some people do, but you don't have to. It's just a review. All I want to see is that you've picked an area, you've carefully read about it, that you understand sort of the big picture of what is it that makes all of this work. And so there's even, you'll see that there's on the syllabus, it has an outline for you. That there'll be an introduction you'll write. So it's an 8-page paper, like a NIPS paper, in NIPS format. And there'll be an introduction with the motivating what the area is. There'll be a section on notation. Then the key results. And you can, if you want, you can put in sort of proof outlines. You might not have room to put in full proofs, but that's a good thing. Being able to synthesize all the stuff and give it kind of an outline of the proof is actually a very instructive thing to do. And then a conclusion saying, comments on the meaning of the results and what are the open questions, what's not known, and so on. So it's a chance for you to synthesize your knowledge in a very focused way in one particular area. And a lot of people, sometimes they come to me and say, what should I do this on? No, you should decide what you should do. I want you to pick something you find interesting. I don't want to assign topics. You can work by yourself or in groups of 2. Okay? And you'll get feedback because there are milestones. So your proposal will be due February 12th, and it's only one page. It's not a big deal. And basically, it's only going to have the title, who you're working with, if anybody, a description of what you're doing, and a reading list. What are the papers you think you're going to need? And by the way, you don't need to read like 20 papers, right? So pick a subset of papers, and how many really depends. I mean, if there's a few small papers, like maybe there's 6 or 7 important papers, that's fine. But maybe it's a really, really complicated subject, and there's 3 major papers that are really long, so then you just read those 2 or 3 papers. It just, whatever, you use your judgment. Okay, and so there's very little to do for the proposal, but I want to make sure you've thought about it and have identified a direction by that time. On March 18th, you'll hand in a 3-page progress report, which will now be a high-quality introduction. What you've read so far, not a core dump of everything, just telling me, what you've read, what you think remains to be done, and so on. It's just forcing you to make sure you haven't forgot about the project and that you are working on it. Then near the end of April, you'll have a first draft due. And the reason why there's a first draft due is because of what we started last year, which was a lot of fun, is we have a conference at the end of this course. So you'll submit a draft of your thing, and you're going to referee each other's projects. This is going to be just like an IPS conference. So you submit it. I'm sure you'll all be, the night before panicking and staying up for a deadline. And then submit it, and then everybody has to referee it, and then there'll be some sort of voting process. And the highest ranked ones will get to present to the class, and that'll be the last 2 classes. And then the TAs and I will be the judges, and we hand out a wonderful prize to the first and second place winners of the conference. It's a lot of fun, actually. Everybody really liked it last year, so we'll probably do that again this year. Okay, so that's an outline of what's in the course. And I'm still just looking to make sure we can fit everybody in. The other thing, again, I would say is I urge everybody to start coming to class earlier because, you know me, I start at, what is this class, 1:30? I start at 1:30 sharp. I always say the most important things in class during the first minute. And so try to get here on time and especially because this is a bit further away. And it's not the easiest class to get a seat in. It's kind of crowded. All right, and the lectures are being taped. So after some time delay, they get posted so you can go back and watch a lecture, or if you're out of town and miss a lecture, the lecture will be available online. All right, that's the introduction to the course. Are there any questions about the course? No questions. That's a good question. They'll definitely be on the course website. I think last year we also put them on YouTube. And so we might be able to do that again this year. Yeah. Yes? You might have said this, but what's a good ballpark for the number of papers to read for the public? It's going to really depend on the area and the papers. So there was some people who found a bunch of short papers on a topic and ended up reading 6 or 7 papers. There was a few people who were reading like 90-page very detailed theoretical papers, and they maybe read 2 papers or something like that. So it's going to depend on the nature of the papers you find. You want to feel like you're covering the area pretty well and covering what you would consider to be the main theorems and results in that area. And if you have any question about it, you can always come to see me or the TAs with a reading list and some of the papers, and we can help you, sort through them and decide what's important. Any other questions? All right. Then I'm going to plunge into the material. And I realize a lot of you have not brought the notes, so that's fine. I'll write neatly for today. But in the future, please bring the notes, because I do make pretty thorough notes so that you don't have to sit there and write things down. And you don't have to write any of this down, because if you don't have the notes now, when you get back home, you can just download them and all the details are there. The first set of notes is just a review, which I'm not going to go through in detail. It's really just to remind you of the main things that you're supposed to remember from 705 and 715, or 701. I'll just quickly state them, but this is going to be very fast because if nothing else, this is just to make sure you remember the key things. So we're going to use a lot of the stuff we did about convergence. And so remember the key concepts, in convergence were convergence and probability. That was the most common type of convergence probably that we use. So you should definitely remember what convergence and probability means. And the other type of convergence we used a lot, of course, was convergence and distribution. And that will also be, again, we made a lot of use of that in 705, and we'll be making a lot of use of that there. So if you've forgotten, just remind yourself what the definitions are. I also am going to freely use our big OP and little OP notation. So hopefully you still remember that, but I know the break, you kill a few brain cells and everything, so just remind yourself if you've forgotten. And what are the two main theorems? Well, there was the law of large numbers, converges in probability to mu, and of course the central limit theorem. So these things are still going to be useful. We'll learn a few other tricks. And then in terms of basic statistics, we did the bias variance trade-off, that the mean squared error is the bias squared plus the variance. This is going to turn out to be much more important this term than it was actually in 705, because for reasons you know from 701, which is when we try to do high dimensional regression, say, or high dimensional classification, we're always going to be involved in this battle of the bias versus the variance. We try to do some sort of regularization. If either the bias or the variance dominates, then we're going to do poor prediction or poor estimation. So the bias variance trade-off is going to be used all the time here. Maximum likelihood we used a lot in 705. It's going to be used much less so this class. So remember, this of course is the maximizer of the likelihood function. That played a big role in our parametric world, but in this course we tend to focus much more on non-parametric techniques, which we touched on, of course, a bit towards the end of 705. So maximum likelihood is going to play a much smaller role this term than it did in the first term, although it may pop up here and there. So just remember, you should make sure you remember how to do maximum likelihood and all the things related to it, like the score function, the Fisher information, and so on. Two topics that we'll study a lot will be regression and classification, or what might be called prediction. So in regression, remember, we have data like this. We get a new pair, and the goal is to predict y from x. And so in regression, this would be real valued. In classification, this would be, say, binary. We may talk about multi-class classification too. We'll see, where x takes many values instead of just two values. We'll see how it goes. And in the regression case, unless I say otherwise, we'll use the same loss function that we used in 705, namely squared error loss. So if we predict with g of x, squared error loss. And of course, the minimizer of this is minimized by, Now, an interesting thing we'll see, though, in this term is because we're going to concentrate on high dimensional problems a lot, is we will be using linear predictors at first, at least, before we do non-parametric. It might seem like an odd thing because really, if the spirit of all of this is to be as non-parametric as possible, why should we use linear predictors? Well, because in high dimensions, it's even hard just to do linear prediction. And so we have to start with linear prediction. And so we will start using a linear predictor, but one thing I want to really emphasize is that we'll be using linear predictors, but never in the course will we assume that the true regression function is linear. We're always going to allow the true regression function to be arbitrary, that doesn't mean we can't use a linear predictor. We can still talk about the best linear predictor like we did in 705, and in this course we're going to talk about the best sparse linear predictor. But we will never assume the truth is linear or sparse. And that's in contradiction to a lot of the research papers where a lot of the high dimensional literature assumes the truth is linear and sparse. And so that's a distinction I'll talk about in detail. And then we'll talk about the non-parametric versions. And it's the same with classification. Remember that the risk of a classifier, unless we say otherwise, it's always just the usual misclassification risk. And we know the optimal classifier is the Bayes, so-called Bayes rule, where it's 1 if the regression function is bigger than a half, and 0 if it's less than a half. And again, we'll start with linear versions. We'll probably do the linear versions pretty quick because I'm sure in 701 or 715 you've done that to death, linear classifiers. Then we'll move on to the non-parametric versions. Okay. And I'll review things as needed. Another thing I want to talk about this year, which will be kind of fun, is although it's not the flavor of the year, I'll talk a bit about boosting. You know, there was a period of time when boosting was the big thing. You remember these days? You're too young to remember this, but it was like, it happens, you know, statistics, there's a new idea that takes over about every 10 years. In ML, it's about once a year, right? So it's like there was boosting. Well, neural nets was the big thing. Then it was boosting. Then it was support vector machines. Now it's deep learning. And who knows what it'll be next year. So things change pretty quickly. Boosting maybe has fallen out of favor, but we'll talk about boosting because there's some interesting stuff to say about it still. It's one of these things where the algorithm, if you haven't heard of it, it's just an algorithm for classification that we'll talk about, but there's a lot of controversy still, but why does it work? And there's the explanation given by Yoav Freund and Rob Shapiro, the originators of it, but there's a different explanation given in the statistical literature. And as I've discovered recently, there's still quite a bit of contention about this. So probably I'll give a lecture about the statistical explanation, and I'm going to ask a colleague of mine who knows quite a bit about the other version, who's give a guest lecture about that version. So we'll talk a bit about boosting. That'll be kind of fun. All right. And there's other things in the review that you can look at your own leisure. You should remember all of these things, and if you don't, just remind yourself. I have a little thing at the end of the review that I put there last year called Why Study Theory. I'm not sure why I put that there. Because if you weren't interested in theory, I guess you wouldn't be here. Or maybe you're forced to be here, some of you. But I do, let me just say a word about that. I mean, some people would say theory isn't important. It's just a matter of building systems that predict well, and who cares why they work, right? Your cartoon, for example, that won the cartoon contest, made that point very well. But obviously, I think there is some value in studying the theory of these things because it helps you answer questions like why is one classifier better than another? It's one thing to say this is working well, but why is it working well? And in particular, when it stops working well, how are you going to know how to fix it if you don't understand why it's working? What assumptions does this work well under? What is the best I can do under these assumptions and so on? So I probably, communicated that in 705, but that's the point of view we take in this course. So hopefully we see that there is some value in theory. On the other hand, I don't want to leave you with the impression that theory is the most important thing, because whether things work in practice or not is really, obviously, of very, very the greatest importance. And something we don't talk about in this course is computation. And that's unfortunate, but really I'm not an expert in computation, so I can't talk about computing time and things like that. But obviously those things are really important. It's great to say this is a minimax estimator, but if nobody can compute it, it's useless. By the way, an open question that's never been answered, if you're looking for hard open questions, is when we talk about minimax theory really is useful, again, just for getting insight, right? It's not that we compute minimax rate and say, oh, now I know how to solve this problem. It's really just trying to get insight into how difficult a problem is. And when we compute this thing, as we did in first term, well, first of all, there's the challenge of even finding this thing, and then there's the challenge of saying, can we find an estimator which achieves this risk? But really, we shouldn't be taking the inf over all estimators. This has actually turned out to be a bit of a problem in the last 2 or 3 years. So when life was simpler and we dealt with lower dimensional problems, we would consider the problem solved in some sense when we could solve this math problem. But what is an estimator? It's an arbitrary function of the data. That's it. This is an inf over all functions of the data. But now when we start talking about complicated problems, so I'll give you a recent example. Principal component analysis. How many of you have done principal component analysis? Okay, not everybody. Well, it's just a dimension reduction technique. We'll probably cover it at some point in the class. But what's happened is that people want to do this principal component analysis in high dimensions. So in the last 3 or 4 years, there's been a lot of theoretical work about sparse principal component analysis. That's the fallback position these days. If you don't know what to do in high dimensions, assume something is sparse. And we'll talk about whether that's reasonable or not. But there's certainly been a lot of work on it. Is if I want to do this dimension reduction subject to some sort of sparsity, can we compute this? And it's taken quite a bit of work to figure out what's the best you can do. What are the minimax risks for sparse PCA? And there's been some work here at CMU by my colleague Jing Lei, for example, has some important papers about that. The problem is you can write down theoretically what this is, but nobody can figure out how to actually compute this because we're taking an inf over all estimators. So mathematically we can solve this problem, but actually finding a computable estimator to achieve it is unsolved to this day. And it's raised the following question. When we do minimax theory, what if we restricted ourselves to a set of estimators that were in some sense computable? I'm leaving that vague. Maybe you mean polynomial time things, maybe you mean something else. And this is pretty much unsolved. There's a few special cases now where people have worked this out. But this would be the coming together of computational complexity and statistical complexity. And I'm just throwing that out there as an open problem. Okay, that's a very interesting question that unfortunately we can't address in this class because nobody has an answer yet. At least not a general answer. All right, so that's kind of the background of where we're heading. You can see that high dimensional and non-parametric are the 2 key phrases throughout the course. So what I want to do then is start some of this background material. Any questions or comments? Okay. What I want to do is just start this background material. And again, I know you don't necessarily have the notes. It's okay. I'll write neatly. But you can look it up. And it's really just background material about function spaces because we're going to use them all the time. And fortunately for us, we don't really need to use a lot of the deep, complicated properties of function spaces. It's an interesting topic. There's courses in functional analysis if you're interested. But we don't need that. We just need really the basic properties of these function spaces. And mainly what you need to know are the definitions. And of only a few of them. So let's start. So we're going to end up working in many cases with a class of functions. So just to motivate that, why in the world do we even need to deal with a class of functions? Well, let's start with regression. So suppose I have n pairs. One way to do regression is to minimize the training error. So just go y of x, y sub I minus g of x sub I squared. And so for linear regression, we take g to vary over the space of all linear functions. And what do we get? If I minimize this over all linear functions, you get, I know you know it. Which estimator pops out? So g of x is varying just over the space of functions like that. You just get the least squares estimator, so that's fine. Okay, that's easy. But now I want to be non-parametric. Here's an idea. Why don't I minimize this over all functions g? What happens? Yeah, I'm just going to interpolate the data, right? That's going to have useless generalization error. We're overfitting. So there's many ways of dealing with this, and we'll see when we do non-parametric regression, there's really two schools of thought on this. One is what I would call localization, which is to deal with the problem locally instead of globally. It's actually, I believe, a better way of doing it for reasons I'll explain. But there's a second approach, which is to put some sort of constraint. It's either regularization or just restrict the class of functions. So the natural thing to do is let's restrict the class of functions. So let's minimize this over some set of functions. And then now the problem is solved, at least in the sense we're not going to get a trivial solution anymore. But the question is, what's a reasonable class of functions? Well, probably we want to deal with smooth functions for a variety of reasons. They're easier to deal with, and hopefully nature is somewhat smooth, and so we might restrict ourselves to smooth functions. So that raises the question, how do I define smoothness? And we'll see that for statistics and machine learning, there's really two types of smoothness classes. One are called Holder spaces, which you can think of is for dealing locally with smoothness, and one is called Sobolev spaces, which is a global notion of smoothness. Okay? But before I get to those two definitions, and those are the two main ones, there's a preliminary notion, which I'm sure you must have come across in some math class you've taken, which is the notion of a Hilbert space. But for our purposes, there's a special kind of space we need, which comes up a lot now in machine learning. This is an example of an interesting sociological phenomena. I would say, 5, 6 years ago, or maybe a bit 8 years, 9 years ago, you couldn't find a paper with that in machine learning. Now it's all over the place. Just do a Google search and you'll see it. This stands for reproducing kernel Hilbert space. And so they're quite popular. And so what is it? Roughly speaking, it's a very general notion of a class of well-behaved functions. So let's review the definition. So we're going to have a set of functions. And first of all, it has to be a Hilbert space. Let me remind you what a Hilbert space is. The details are in the notes, but just remember, basically it's a complete inner product space. It's got an inner product on it. Okay, that's the key thing. And so let me just, the usual examples would be if I take RD and we use as an inner product the usual that's okay. There might be, if you want a seat, there's one right there. Yeah, I tried to get them to sit in the seats, but so I may not be able to clear the waiting list, but we'll talk about that at the end of class. So, RD with the usual inner product, and of course an inner product defines a norm, because the norm of this. So that's the simplest Hilbert space. The set of functions mapping 0, 1 into R, and such that they have f squared integrated as finite with the inner product that's another familiar Hilbert space. Okay, but the thing about Hilbert spaces in general is that they can contain lots of unsmooth functions. And in particular, let's look at this space. Suppose I had, what does it mean, first of all? In a Hilbert space, we have to be careful about the notation. What does it mean to say that fn, a sequence of functions fn, is converging to another function f? What we mean by that is that the norm is going to 0. So here's a question. And this gets to the issue we're concerned about, which is dealing with well-behaved functions that we can estimate. If fn is converging to f, does that imply that at each x, fn x converges to f of x? No, it does not, right? And that's because of things like this. where we might have a sequence of functions. Say the function looks like this, but then as n gets bigger, I make it get very, very tall and thin. And so the L2, if I take fn minus 0 squared, I can make that go to 0 by making this area go to 0. But look at the value, say at 0, it's shooting off to infinity. So that would be an example where the integral of fn minus fn squared goes to 0, but at the point 0, they don't converge. But that's because I'm allowing a very spiky function. You might say that a well-behaved function a class of well-behaved functions shouldn't contain functions like that. And that's what a reproducing kernel Hilbert space is. However, I realize that I've already jumped ahead in the notes. So before I get to reproducing kernel Hilbert spaces, I forgot to cover some of the material. So a Hilbert space is just an inner product space, space of inner product, and complete. It's closed under limits. Okay. A reproducing kernel Hilbert space is a very special one, but we haven't got there yet. I just jumped ahead in the notes. First, I need a couple of preliminary definitions before I get to the reproducing kernel Hilbert. In fact, the reproducing kernel Hilbert spaces are precisely the spaces where this will be true, but we'll get there in a few minutes. First, I need to remind you, and some of these things I'm sure you know already, as LP spaces we're going to make use of quite a bit. So an LP space, we could define this on any subset, but let's say on an interval AB, will be the set of functions from there with the following norm. So it's just this raised to the power of p. Where p is some positive number. So we're going to have reason to use various LP spaces, as we'll see throughout the course. One rule of thumb, though, is if I don't put the p there, so if I just write this without the subscript, you should assume I'm talking about L2. This is the LP space, is this set of all functions for which this norm is But if I don't write what it is, just assume it's L2. That's going to be the most common space. We'll use LP spaces of other P's sometimes, but I'll try to remember to make sure I let you know that when it's not 2. If I don't say what it is, assume it's 2. Okay? Now, L2 spaces, of course, are pretty special. For one thing, they're not just an LP space, they're a Hilbert space. That's the special LP space that happens to be a Hilbert space. And in fact, we're going to be dealing with another property of these spaces that, and hopefully this is a review, but if I take the space L2, we know I can construct a countable basis for the space, many different countable bases. So remember that an orthonormal basis, let me use the same notation that I used in the notes. I used phi. So will be any sequence of functions where these have norm 1 and they're orthogonal. Okay, and so there's lots of these. What's an example of a orthonormal? This is an orthonormal basis. What's an example of an orthonormal basis for L2? Fourier basis sines and cosines. How about polynomials? If I just take x squared, x cubed, well, not quite, right? Because they're not going to be orthogonal. But I could always take each polynomial and orthogonalize it with respect to the last one. Now I get the Legendre basis. So there's lots of them. Wavelets. And how many of you have dealt with wavelets? Okay, just smaller subset. That's in signal processing a very important basis. This is wavelet basis. We may or may not talk about wavelets. I actually have an example of a wavelet basis here, but that's not so important right now. And the important thing anyway about a basis is having selected a basis, we can always expand one of the functions in the space in terms of these basis elements. That's even one way of doing nonparametric regression and density estimation, is to expand it into a basis and then estimate the coefficients. The coefficients are just the inner product. These are the Fourier coefficients. It's just the inner product between the function and the jth basis function. So hopefully this is something you remember from calculus. You can always take a function in L2, expand it in any basis you want, and reconstruct it. And if you know the coefficients, you know the function. And there's many, many examples. In the notes, I have lots of examples of different bases, which will, if we need them, we'll talk about them. I'm sure we'll need them at some point in the course. Sometimes the basis, a convenient basis, might not be so obvious. So like when we talk about some of these nonparametric regression problems, we might want the basis to satisfy a bunch of conflicting properties. All right, so those are the background things, is what's a Hilbert space, what's an LP space, what's an L2 space. Now I want to define a Holder space. So this is the first kind of one with any statistical value to us. And when do we use this? And I'm going to tell you right now. Anytime we're doing some sort of smoothing method, like for a locally based method. So for example, estimating a regression function, we're going to often talk about using a local average, or a classifier using local properties of the regression function, or a density function. And in order to prove things about this, doing it without any assumption at all in the function is very difficult. Sometimes you can, but sometimes we can't, and we need to make some sort of assumption. You might want to assume some sort of basic smoothness property, and this is when we often use Holder spaces. One thing to be really careful about in all of these assumptions is their assumptions. So when I say, we'll assume we're dealing with a class of Holder smooth functions, it's an assumption. And sometimes these assumptions are not innocuous. But let's suppose I have, let's do it on the real. I'll start with the version on the reals. And Holder smoothness. So there's going to be, this is the smoothness parameter. This is going to be like a ball in a function space, because think of it as a ball. This is how much smoothness there is, and this is how big the ball is. Okay, and it's the set of functions, G, satisfying the following condition. That if I look at, so for our purposes, beta is going to be a positive integer. 2, 3, 4. There is a definition for fractional things, and which I did last year, and I realized I never used it once in the course. So we're not going to bother defining the fractional version because we don't need it. So think of this as 3. All right, and we're going to what it's going to say is just that the derivative one less, and there's by the way, different papers use slightly different definitions. This is the definition that we're going to need. That if I go one value less, that the derivative of that order is Lipschitz. That's the definition. So if I take the beta minus 1, so if this is 3, this is the second derivative. Okay, and we want that is less than Lx minus y for all pairs x and y. Okay, so in fact, if beta was 1, this is just the definition of the set of Lipschitz functions, because this is just the function itself then. The most commonly used one in most theoretical papers on machine learning and statistics is beta equals to 2, which really, just to write out what it is, it's just saying that the derivative is Lipschitz. It's essentially like saying there's a second derivative. So this is just saying that this is the holder 2 space. And a lot of things that you want to prove are true by assuming sort of basically that it has this minimal amount of smoothness.
Sorry, you might have said this already. Is L is just a constant?
L is some fixed constant, positive constant, right? Okay. Modulo some small details. If I just divide through by x minus 1, I take the limit, that's like saying that the second derivative is bounded. It's not quite true, but just think of it as saying that it's basically like there's 2 derivatives. So that's the most commonly used assumption in a lot of the theory. Doesn't make it true. And that's something we always want to be aware of. But we will make this assumption all the time. The important thing is to understand when you're using a method, oh, it requires holder smoothness. It's not that it's necessarily that the truth is holder smooth, but at least you know a certain method might require holder smoothness. There is a multivariate version that we're going to need, which is just that the higher order derivatives satisfy the same property. So the notation we'll use is I'm going to write ds, where s now, what's going to happen here is s, suppose we're in a d-dimensional space. So I'm going to have to specify d indices. This is just saying like the mixed partial derivatives or the second derivative of the first coordinate. So the second derivative of the first coordinate would be like 2, 0, and so on. So this is going to be, in other words, this is d sd with respect to x1 to the s1, x d, the xd. And so we're simply going to require that these higher order derivatives also satisfy this Lipschitz condition where this is 1 degree less. So I'm going to write this as that. By that, I just mean the sum of these indices. So it's just saying all of the, what we had for one derivative here, now this has to hold for all of the, the second order derivatives, third order, whatever order we're up to. The higher beta is, the more smoothness we're demanding. And the connection with all of the, yes?
Don't you have matrices on the left hand?
No. Yes, well, I see what you're saying, yes. But what I want this to do is I want this to hold for all of the mixed partial derivatives. So I should have written for all s. I want this to hold for each s. So for each such. Do you know what I mean? Like the second partial derivative this holds, and the other second partial derivative this holds.
Each element of the
Yes. Oh, that's just beta minus 1 here.
No, on the right hand side. You're still dealing with G from.
I'm still dealing, sorry.
Target is still R, right?
Yes, so just to be clear, this is a one-dimensional function. It's just that t, sorry, maybe I confused you. T is an RD. Yeah. But what's the connection here with statistics and machine learning? Do you remember in 705 we often saw the following rate? We saw rates that look like this. In fact, let me do the squared error version. If we dealt with squared error, it looked like this. What we're going to prove later in the course is that for regression, classification, density estimation, in a space of this type, when we get to minimax theory, we'll see that the minimax rate looks like this. And if you think about it, what it's saying is the beta, remember, higher beta is more smoothness, so you get a faster rate. On the other hand, the bad news is cursive dimensionality. When as d gets bigger, you get a worse rate. This rate, If there's one rate, you're going to remember this is just is going to come up all over the place.
But why in this single value we do not require for any s, only base minus 1?
Well, yeah, why did I write it that way? Maybe I... why did I require it that way? That's a good question. Oh, no, because I'm doing this, though, for all possible s's that sum to beta minus 1. I should have said that. Or it's actually less than or equal to, but we'll say equal to. So that was a little bit unnecessary.
So these things are nested? That's just one.
Yes. So I think something, what I should have gotten beta minus 1. What did I do wrong?
You're right. You're just like saying more than.
No, because you said it can be less than equal to, that's why you need the.
Yeah.
When you're taking s derivatives, you're assuming that.
Right. This is this. Yes. Right. So this is fine. This right. This is 1. I was trying to be. I just put it more generally. I'm trying to remember whether I need that or not, but we'll just leave it like that for the moment, and I'll check that. Okay. So for any time we prove something about the behavior of a function at a point, you're going to see in almost all literature people assume Holder smoothness. Why? Because frankly, it's the most convenient assumption to be able to prove things, to be very honest with you. Okay. But now there's a different notion, which is a more global notion of smoothness. And this is when we're proving things about, for example, in L2. So for example, suppose you had an estimator and you wanted to get the minimax rate in L2. That's saying something about the integral of the whole function. And so it's natural that people would use some notion of smoothness that involves the integral. And that's what a Sobolev space is. So there's various ways to define a Sobolev space, but we'll just use this one. A Sobolev space, and there's 2 parameters in general, although we won't need the full generality. Let's do it on 0, 1. So it's the set of all functions let's say on LP 1, so that the p norm is finite. Now there's a technicality here I've got to tell you about. So that the derivatives, this is the mth derivative, is also. So one small detail is that we don't actually require the functions to be completely differentiable. It's enough that they have something called a weak derivative, which means that I can write the difference of the function as the integral of a derivative. And we can talk about higher order weak derivatives. It's a small technicality. Roughly speaking, when I say a Sobolev space of order m, we mean that the mth order derivative, its integral is going to be bounded.
And the functions are compactly supported, are on 0, 1.
I'm doing it on 0, 1. That's correct. I should say in general, like even over here, if you start talking about like open sets, then you have to talk about how it behaves at the boundaries. There's actually choices you have to make and so on. So for now, just say on some fixed closed interval.
Why do you write a norm here? A norm of the derivative.
Yes. It should be the, well, I should, yeah, why did I do that? You're right. Thank you. Okay, this, I don't think, so there's 2 things going on. How many derivatives are well behaved? and behaved in what sense, in which norm? The pth norm, the mth derivative. But I don't think there's anywhere in this class we're ever going to need the full generality of this. We're usually just going to use the 2 norm for the derivatives. So generally speaking, if I write Wm, we mean Wm2. So intuitively, that means if I take the mth derivative, square it and integrate it, it's finite. And that's a measure of smoothness, right? If a function was too wiggly, then when I take, say, its third derivative and square it, it could blow up. So this is a more global measure of smoothness because we're integrating it across the whole space. And you're going to see whenever people prove things about minimax theory or rates of convergence involving like an L2 norm or something like that, they typically assume it lives in a Sobolev space. All right. Yes. So now I make reference here to a kernel. I'm just wondering whether I should come back to that when I get to the reproducing current Hilbert spaces. So theorem 2 says that the Sobolev space Wm is a Hilbert space. In fact, it's a reproducing current Hilbert space with a very particular norm and a very particular kernel. But probably we'll come back to that after I've gotten to the reproducing kernel Hilbert spaces. I think that was jumping the gun a little bit there. There's a related notion, though, that I want to talk about, which comes up a lot, again, in minimax theory. Which is the notion of what's called a Sobolev ellipsoid. So what's that? I'm going to consider a sequence now, this is not a function, this is just a sequence of real numbers. Okay? And I'm going to consider this thing, which is called an ellipsoid, which is simply, yeah, I'll do the 2 version, but this is bounded, where let's take aj squared, actually let's take it to be equal to the 2m. So these let's take a look at this. These j's are exploding. So in order to stay finite, these must be decreasing. What has this got to do with anything? Okay.
Pi times j? That's pi times j?
That's pi times j, yeah. Yeah. Okay, so if I take a set of functions, say a set of functions on, let's say, periodic functions on 0, 1 in L2, and I expand them in the Fourier basis, they form a Sobolev space if and only if the coefficients satisfy this condition. In other words, remember I said you could take a function and expand it and look at its coefficients. Checking whether the function is in the Sobolev space is the same as just checking whether its coefficients die off fast enough. Right? If these coefficients died off slowly, this would blow up. This is one way to see that Sobolev space correspond, in some sense, to smooth functions. Sorry? Pi is 3.14159. It doesn't actually have to be that exact number, but
You could have defined it using any base. You're here using the trigonometric.
yes, I'm just for convenience, this is to make the relationship with exactly with the trigonometric basis for simplicity. Sorry? So that's a good question. M is, again, the number of smooth derivatives. And is it a parameter is a good question. If I say it's in a Sobolev 5 space, what does that mean? It has 5 well-behaved derivatives. So there's 2 types of results we'll see. Some results assume a certain amount of smoothness. That's the most common ones. Then there are methods which are called adaptive methods, which try to adapt to the amount of smoothness, which we may or may not cover in this class. We'll see. For most of the course, we're just going to assume a certain amount of smoothness when we prove things. But it really should be a parameter. Okay, so I've really barely, touched the definition of these spaces. We don't need a lot about these spaces. Okay, this is just because I'm going to mention them a lot throughout the course. And there's more details here that you can read if you want. There's also a starred section that I'm not going to cover called Bessoff spaces. I only put it there because some of you may be familiar with wavelet methods. And one of the advantages of these things called wavelets, which are very special bases, is that they produce very good estimators in these function spaces called Bessoff spaces, which are much richer spaces than Sobolev spaces. This attracted a lot of attention for a while. It was one of these hot areas, and in signal processing it probably still is, but in statistics and machine learning I think they've already fallen out of favor. So, because the truth is they don't work well in practice. And so I'm not going to cover it. 5 years ago I actually went into details about this stuff, but if you want to read it, it's there, but we're not going to cover it. Okay, let's keep going. Let's now finally talk about, do I want to mention that? Let's just go right to finding these reproduced in kernel Hilbert spaces. So you would have come across these in 715, and I would think 701 as well. So the idea here is we want to construct a nice class of functions in a very convenient way that's going to have nice statistical properties but also be easy to compute with. And that's the main reason why people use reproduced in kernel Hilbert spaces. And as the name suggests, it's a Hilbert space with some special properties, and underlying it is this special function called a kernel. Now, here we get some potential confusion because the word kernel is used for 2 different things. So kernel is used in this sense to define a reproduced in kernel Hilbert space. So those are usually called Mercer kernels because of Mercer's theorem. Unfortunately, there's another use of the word kernel, which is when we talked about kernel density estimation in 705 and when we talk about kernel regression, which is something, remember, we use to do local smoothing. So I'm going to try my best to make sure whenever I'm talking about them I'm clear about which one we're talking about. To make things even more confusing, it's usually the same kernel. It's usually a Gaussian. So, I mean, the classical example of this, is just something like this. But there's lots of other kernels, which is what makes them useful, is that you can define kernels in many different ways. So right now, if you're familiar with kernel smoothing, I'm not talking about that. I'm just talking about this function. And it's got to satisfy a couple of properties. It's non-negative. It's symmetric. And most importantly, it's positive semi-definite. So what that means is if I take any finite set of points and any real numbers, then it's just positive semi-definite as if it was a matrix. So in other words, let's say I take an arbitrary set of points of arbitrary size, let's say size n, that this is always bigger than or equal to 0. For any choice of points x, so let's think we're on the real line, we're defining a set of functions, pick a finite set of points x1 to xn, pick some real numbers c1 to cn. In other words, this is just saying if I take this kernel, which is a function, but if I evaluate it at every pair of points, I get a matrix. Let's call the matrix K. I'm just saying that as a matrix, this has to be positive semi-definite. But that has to be true no matter how I choose the points. Okay, and then we say that this K is a positive semi-definite kernel. Okay, and the Gaussian is a good example. And we're going to use this to define a class of very well-behaved functions. Interestingly, these were first introduced by Grace Waba and Emmanuel Parzen in the 70s in statistics, and then kind of got ignored for a long time, and then kind of resurfaced in the machine learning literature maybe 10 years ago or something like that. And now they're very common. So the idea is we're going to build a function space, a reproducing kernel Hilbert space, from this kernel. And the question is, how do you specify the kernel? That's part of the art, is that depending on the application, you have to specify a good kernel. So we're assuming here somehow the kernel is given. Just to have an example in your head, again, just think of the Gaussian kernel. But first we need the following theorem, which is Mercer's theorem, which is that if we have a positive, definite, symmetric kernel bounded, I'm going to assume this is bounded. Okay. Now we cannot, and we want to think of this kernel now as taking a function and producing a new function. Think of it as an operator. In other words, I can define tk, an operator which takes a function as its argument and outputs a new function. And the value of that function at x is simply the integral over whatever the space is defined in. Okay, so I just take a function and integrate it with respect to the kernel. That changes the function. I get a new function. So think of it as a mapping of functions to functions. And it's positive semi-definite, remember. So another way of saying that, by the way, is that for all functions, this is positive. All right, then first of all, we can define the eigenvectors and eigenvalues, except they're not going to be vectors, really, they're going to be functions, right? Just like a matrix. If K, look at this matrix. I can, you remember back to linear algebra, I can talk about its eigenvectors and eigenvalues. You can do the same thing here. It's just that they're going to be functions. So instead of matrix multiplication, we're going to have integration. Right? So just replace the integral with matrix multiplication. You'd have the usual definition of eigenvalues and eigenvectors. Similarly, we can do this with the integral. And this defines a set of eigenvalues and eigenvectors. And these exist. These have a finite sum. The eigenfunctions are in fact bounded, but most importantly, we can rewrite the kernel as a sum of these eigenfunctions. So those of you who have seen this before, you know that these are going to be the implicit high-dimensional features.
Why does that integral then exist? The one up right, the kxy, fx, fy?
It's a theorem. So
Part of the assumption.
yes.
Okay.
No. I think it's a result. So, no. We're assuming it's positive definite. So we're assuming this thing is always greater than or equal to 0. And
Positive definite would be that one. I think this is a stronger. Isn't it?
yeah, actually, I think it's still true. I think that implies this, if I remember correctly. Assuming that k is positive definite, we're on a subset of the reals. Is this a stronger assumption? The question is than that this holds for every finite set of points. But I'm pretty sure that that actually implies this. I have to check.
It's just the monotone class theorem, isn't it?
It's the
You start with like indicator functions.
right.
and
So
then-
you just take the limit. I think it's going to be true. Yeah.
I mean, you need to say like what kind of measure you're using here.
So technically, I didn't write it here. This should really be Lebesgue measure, for example. But yeah.
Well, as far as I recall, there is a counterexample, but
Okay. Well, you might be right. My recollection is that implies that, but I'm just going by my memory, which is notoriously bad. So you could be right. So we may need, if that's true, then we need an extra assumption to make it true. But the question is now, I guess we won't have time for this today. So that's all. We're finally in a position to define what we mean by this reproducing kernel Hilbert space. What we're going to do on Thursday then is just basically think of these almost like basis functions. So if we fix one value of this is just a function of one variable. And if we take a bunch of functions like that and take linear combinations, we get a space of functions, and that's going to be the reproducing kernel Hilbert space. And different very familiar spaces turn out to be reproducing kernel Hilbert spaces with different kernels, sometimes not obvious kernels. So bring those notes on Thursday, but also bring the next notes, because we're almost done this. We're going to really start the real material, which is concentration of measure, on Thursday. Please try to get here a bit earlier. And I'm going to have to sort out, so I was going to clear the waiting list, but I think that's premature because it looks like we are a bit oversubscribed. Let's see what happens in the next class or two.